Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the concept of electrical safety, where we will learn about electrical hazards and the safety precautions using a trip switch, fuse, and earth wire. In this lesson, we're going to just go through some really basic stuff because whatever we're covering is for the students who are going to be taking the Cambridge IGCSE Physics. So whatever we'll be going through is only what students will need in their syllabus. Now, as we always know, Miss Hu's slides are not complete without a meme. So when we talk about electrical safety, no, this is not what you do. So now let's go into what we really need to learn about electrical safety, starting first with electrical hazards. Now in your syllabus, you need to know about the following 4 hazards: damaged insulation, overheating cables, damp conditions, and excess currents from overloading plugs, extension leads, single and multiple sockets. What we'll go through is an explanation as to why each of these are considered electrical hazards, starting first with damaged insulation. So damaged insulation here refers to the plastic or rubber covering the wire. So if there's any problem with the covering which causes wires to be exposed on the inside, this can cause an electric shock or a short circuit because the wire that's carrying current inside can come in contact with a human being or with another conductor. Next, in terms of overheating cables, the overheating of cables could be due to excessive current that flows through the cables, causing it to get very hot. So when the cables get too hot, it can cause the insulation to melt and can cause the risk of an electrical fire. Damp conditions refers to the presence of water, so for example in a bathroom or even on a wet ground. So as you should know by now, water conducts electricity. So in damp or wet conditions, this can cause current to flow, which increases the risk of electric shock. Now, for excess current from overloading plugs, extension leads, single and multiple sockets, this happens when you plug in too many devices onto the same socket. When this happens, too much current will be flowing from that socket, causing the wires to overheat and can cause an electrical fire. Sometimes when you overload a socket, you'll find that can cause a mini explosion and cause the socket to be spoiled and can't be used anymore. So that is why when you want to connect many devices to the same socket, it is possible, but only if they're drawing very little current. So for example, if you're charging a handphone. But if you're plugging in a device that draws very high current, for example a refrigerator or an air conditioner, you cannot plug multiple devices into the same socket. Each of those high-powered devices must have their own socket to draw current from. Now, let's go into some of the safety features. So in this lesson, we will learn about the trip switch, fuse, and earth wires. Before we go into each of these safety devices, let me give you an overview first so that you have an understanding of what they are and how they're used. So you're going to have to bear with my drawing for a little bit. So you'll find trip switches at the entry point of houses, buildings, or rooms. The trip switch is also known as a circuit breaker. So let's say we're looking at your house. So as you know, as electricity transmission is carried in through cables into your house, and at the entry point of where current flows in, there is the trip switch or circuit breaker, or sometimes they call it a fuse box. So the circuit breaker will control the amount of current that's flowing into the house before it is distributed into the many different rooms and devices in your house. Now let's say you are charging your laptop or your tablet. So imagine that this wire is going through the walls, and then of course you plug in your laptop charger to the wall. So I'll just write here, trip switch. And where your plug is, in your plug, there will be a fuse. So the fuse will control how much current is flowing into the devices. Some devices have earth wires. There'll be an earth wire to channel the excess charges into the ground. So that means on this slide, you can see that there are 3 levels of protection. The trip switch or circuit breaker provides the first level of protection, which blocks any overcurrent into the house or building in the first place. Now let's say the high current is able to bypass the trip switch. Then the fuse acts as a second level protection, which blocks overcurrent from entering the device. The earth wire acts as a third or additional layer of protection, which channels the excess charges into the ground. So it is important to have as many levels of protection as possible because you never know, any point could fail within this kind of circuit. So that's why we have to learn about all 3 in the syllabus. Let's go into more detail about each of these safety devices, starting first with the trip switch, also known as a circuit breaker. So a circuit breaker is a safety device in an electrical circuit that automatically interrupts the flow of electricity when the current flowing through it is too high, such as from an overload, short circuit, or lightning strike. I'm sure you've seen this in your house somewhere. So every house should have one of these, every office, every building, and sometimes in a building, every room has this. So for some of you, you'll find that in your school, every classroom may have one of these as well. So you might find that the trip switch in your house has many of these levers because each of these connections will be connected to a different part in your house. For example, it may be connected to different rooms in your house. Each of these connections have a maximum current which is allowed to flow through. If the current that's flowing through that particular connection is too high, then the switch would trip. So that's why we call this a trip switch. That's why you'll find sometimes when you plug in a faulty device, that room goes into a blackout, but not the rest of the house. So when that happens, one of these switches would trip downwards. In order to regain electricity flow, all you need to do is push the switch back into the on position. Sometimes if the entire house trips, then there is one main switch which blocks all the current from flowing. All you need to do is switch on that main switch so that current can flow into the house again. So a high current can flow because of an overload. For example, if you plug too many devices into the outlets in that area, a short circuit within a device which causes the current flow to be too high, or sometimes from a lightning strike. So that's why some of you might find during a thunderstorm, your house goes into a temporary blackout because lightning has struck the wire that's carrying current into your house. So as a safety shut off, the switch would trip. Now, how does a trip switch work? There's an electromagnet in there which causes the connection to be cut off when the current flow is too high, causing the magnetic field to be too strong and attracts one of the armatures in such a way that it disconnects the current, causing the switch to trip. So when you push the switch back into position, what you're doing is you're pushing the armature back into the connecting position, allowing current to resume. If you'd like to know more about how a trip switch works, I will cover that in a separate video under the concept of electromagnetism. I'll put a link to the video in the description below. So a circuit breaker is necessary because if the current flow is too high, it can cause an electric shock or it can spoil the devices that are connected to the power socket. Because if the electric current flow is too high, they can cause all devices that are connected to the wall circuit to spoil because too much current is flowing, or can cause an electric shock if the current happens to flow through a human being who is in contact with the electricity. So the trip switch or circuit breaker is placed at the entry point of where current flows into that zone. So the circuit breaker is the first level of safety in a house or in a building. The second safety level is a fuse. A fuse is a safety device in electrical circuits that protects against overcurrent. It contains a wire or a strip of metal that melts and breaks the circuit when the current exceeds a certain level, preventing damage from overheating or short circuits. So for example, you can see in the diagram on the left here, every fuse has a current rating. So the value that's written on the fuse is the maximum current that is allowed to flow through the fuse. For example, 3 ampere, 5 ampere, and 13 ampere. If the current was to exceed this level, the wire inside would melt, breaking the current flow. So the current can no longer flow through the fuse. So fuses are sacrificial devices. Once they're blown, they need to be replaced. They cannot be fixed or reused. So this is a symbol for fuse. So we have a line here that represents the wire that's inside the fuse. Now before we go into more detail about how a fuse is used, let me first show you how we determine the value of the fuse that should be used for different devices. So in this example, we need to determine the value of a fuse that should be used for a 600 watt electric motor connected to a 240 volt supply. First of all, you need to calculate how much current flow is needed for the electric motor to function. We have the power value here at 600 watts and the voltage of 240 volts. We're going to use the electrical power formula, which is P equals to IV. So P is 600, I is unknown, and V is 240. When we calculate the value of the current, you should get 2.5 ampere current. Now, this current value is not the value of the fuse that should be used. This is the value of the current that should be flowing through the electric motor for it to function optimally. So the value of the fuse that we should choose should be higher than this current. If we were to choose a value that is lower or equal to the value calculated, what happens is that the fuse would blow or melt before the current is able to flow properly through the device. So for example, if you were to pick a fuse value of 2 amperes, the fuse would melt before the current can even reach 2.5 ampere, which means that the motor will never be able to function optimally. So you need to select a fuse that is higher than this value of the current. However, you don't want to pick a value that is too high, because that means that a very high value of current can flow through the device and cause the device to spoil. So for example, if the optimal current value is 2.5 ampere, you cannot pick a 13 ampere fuse because, as you can see, the current value is too high, which means that the fuse would allow up to 13 ampere of current to flow through the motor, and that could potentially spoil the motor. So what we want to pick is the value of a fuse that's slightly higher than this. Now when it comes to fuses, there are actually fixed values of fuses for us to select from. And this is because the manufacturers cannot be making a wide range of different values of fuses. So normally the set values of fuses, typically 3 ampere, 5 ampere and 13 ampere. Don't worry, you don't need to memorize these fuse values. You would normally be given a selection to choose from when answering the questions. So in this case, we would pick the 3 ampere fuse because it is just above the value of the current needed. We don't want to pick a value of fuse that's too high because that excessive current could end up spoiling the device. So we're going to select the fuse value of 3 ampere. Let's take a look at another example. Now we need to determine the value of a fuse that should be used for a 1.8 kilowatt air conditioner connected to a 240 volt power supply. Now to solve this, again, we're going to have to calculate the current first. So using the electrical power formula of P equals IV, so 1.8 kilowatts is actually 1,800 watts. Current is unknown, while V is 240. Calculating I, we get 7.5 ampere. So now here's the tricky thing. We just learned that we need to select a fuse value that's just above the current value needed for optimal operation of that device. So given this current value, most students would say, okay, we need a fuse value of 8 amperes. The thing is, 8 ampere fuses do not exist. So most manufacturers would only manufacture 3 ampere, 5 ampere and 13 ampere fuses. So based on the reasons we have earlier discussed, we cannot choose fuse values that are less than the current value. So you cannot select 3 ampere or 5 ampere, which means that the best possible option here is a 13 ampere fuse. So this has confused students because doesn't this go against what we've just learned? We're supposed to select a fuse value that's just above this optimal current value. We are limited by what is available for purchase. So how come 13 ampere fuse is accepted in this case? It is not ideal, but given this situation, most manufacturers of the device, that means of the air conditioner like this, would have to allow current to flow through the device up to 13 ampere without the air conditioner spoiling. So 7.5 ampere is ideal, but the device still allows up to 13 ampere of current to flow through without spoiling the device. So this is how we can select the values of fuses that should be used in different devices. Now let's take a look at the 3-pin plug. Now the 3-pin plug that we can see on this slide here is actually based on the British standard. Not all countries use this 3-pin design. Many different countries have different types of plugs. For example, in China and in Indonesia, they use 2-pin plugs. Some of these 2 pins may also look different. Some may be round and some may be flat. Only some countries use the British standard, for example, Malaysia and Singapore. Because we're learning Cambridge IGCSE, we will be learning about the British standard, so we'll go through the British 3-pin plug. So if we were to open up the 3-pin plug, this is what it would look like. So you can see here, you have the pin on the top and the 2 pins at the bottom here. The pins are not where the screws are. Let's have a closer understanding of how the 3-pin plug works. So the 3 pins are actually here, here, and here at the bottom part of this tube. This tube is actually the fuse. I'm just going to erase the circles I made. Now, you can also see over here that there are 3 wires and each wire has a different color here. So it's color coded so that it's easy for us to determine where each of these wires are actually connected. So the brown wire is connected to the fuse. This wire is known as the live wire. Where the fuse is connected, it's always to the live wire. So you can see from the connection here, the current will flow through the fuse like this first before it flows into the live wire. So when you look at this diagram, you should be able to see that current will flow in through this pin, through the fuse first, and then it will flow through the live wire. The blue color wire is known as the neutral wire. So what's the difference between the live and neutral wire? So the blue wire is known as the neutral wire. So what's a neutral wire for? Basically, if you take this 3-pin plug and you connect it into the wall socket, your wall socket would be providing alternating current power supply. So let's say this circuit represents how the device is connected to the alternating current power supply. If let's say this represents the fuse here is connected to the live wire, while the neutral wire would be the wire that's connected on the other side of the device. So what's the difference between the live and neutral, and why does a live wire have a fuse? So you have to remember that for alternating current does change direction. So there's no fixed positive and negative terminal. Current would flow one way and then the other way. But there's always a first initial current flow coming from the power source. So if we were to do a quick sketch to help us visualize this, if this was to represent the alternating current power supply that will be provided to our households, the first flow, that means the first half cycle here, that would be where current is first flowing in to the device through the live wire. The neutral wire allows the current to be completed. And yes, during the second half of the cycle, the current would then flow the other way, that means through the neutral and then through the live. But why it's so important to put the fuse at the live wire? Because that's where the current first flows through. So if there's any problem, for example, if there's too much current flowing into the wires that could potentially spoil the device, the fuse needs to stop the current from flowing. So that's why the fuse is always placed at the live wire. So remember, the fuse and the live wire is connected at where the current first flows from the power supply. Now the device only needs 2 wires to complete the circuit. So why is there a third wire? So the third wire is not present in all plugs. Not all devices need the third pin. That's why in some countries they don't even have the option of the third pin to begin with. The third wire, as you can see here, is both yellow and green. This wire is known as the earth wire. The purpose of the earth wire is to channel any excess charges that could be accumulated in the device down to earth. For example, if there is a short circuit, if there is a device fault, the excess current needs to flow somewhere. So rather than keep it inside the circuit, they put it down to earth. The symbol for earth wire is basically like this. That means this goes down to the ground. So this part here represents earth. So why does it flow down to earth? Because you have to remember that earth has an iron core, making it some kind of conductor. So any excess electrons would be flowing down to earth. So the earth wire is also considered to be a safety device of sorts because it channels the excess charges down to earth so that it won't spoil the device, or if anyone comes in contact with the faulty device, the charges won't flow into that human being. Instead, the charges would flow down to earth. Now, some additional safety precautions that you should know. So the outer casing of an electrical appliance must be non-conducting or earthed, because if a live wire touches the casing, it could become live, giving a dangerous electric shock, while earthing or insulation can prevent the user from receiving the shock. So, for example, if you have an electric kettle, the kettle actually draws a lot of current because it requires a high value of current to produce that high value of heat. And the same thing also applies to a hairdryer. You'll find that these kind of devices tend to be made out of plastic because plastic is an insulator. So that way, if there's any short circuit, for example, if let's say the wire inside the kettle was broken and accidentally touches the surface of the kettle, if the kettle was made out of metal, it's possible for the metal surface to conduct current. So if a human being was to touch that metal surface, they could get an electric shock. But because plastic is an insulator, even if the wire comes in contact with the plastic will not conduct electricity anyway. So there will be no risk of electric shock. That's why most electrical devices are made out of plastic. For example, a hairdryer as well. So if the earth wire is present, that earth wire would help to ground all the excess charges. If there's plastic insulation, it can prevent the user from getting that electric shock. Now, without the earth wire, it's still possible for the device to be used, but whichever the case, a fuse must be present at all times because a fuse protects the circuit and the cabling for a double insulated appliance. The term double insulated here refers to the insulation around the cable as well as the insulation on the device itself. For example, using a plastic casing on the kettle or the hairdryer. So once again, we're just going to look at the UK plugs. We already know that UK 3-pin plugs have fuses in them. And the third pin on the top is for grounding, which is where we connect the earth wire. Now you might sometimes see 2-pin plugs, and for the British standard of UK 2-pin plugs, they still have fuses in them even without an earth wire. So you'll find that 2-pin plugs are normally used for double insulated appliances only, because without an earth wire, it is still relatively safe to use because of the double insulation. Now, just to share a quick note about other plugs. This is not quite in your syllabus, but it's good for general knowledge. Not all plugs have fuses. In fact, quite a huge number of countries do not make it a standard requirement to have fuses. So for example, plugs in China, Indonesia and EU do not have fuses. Is this still safe? Yes, because there are other safety precautions that have been implemented due to the different ways the circuits are set up. So why we're learning about fuses and earth wire, even though a lot of countries do not implement this? Because Cambridge is from UK and we're learning the UK syllabus. So that's why. And that is it for this video. So if you found this video to be educational and helpful, do click like and let me know in the comments below how you have found this video to have helped you. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do watch my videos on other topics on my YouTube channel, which you might find helpful. Subscribe for more free physics lessons from your physics teacher, Miss Ho. Happy studying!